Thermodynamics is the science of energy and how it moves and transforms. Before we get to the relationship between thermodynamics in life and physiology, we have to go over a few basics. We start with a theoretical device called the universe. We have to clarify that word a little bit. As we're using it here, a universe is simply a closed thermodynamic system, that is, one in which energy can neither enter nor leave. Whatever's there is it. Also, the universe need not be any particular size. The universe can be big, as in the universe, or it can be as small as a cell or even a collection of molecules. The only requirement is that the universe can be treated as if it's thermodynamically closed. That is, it can't tap into energy from outside itself or dump energy out of it. Such a system is called a closed thermodynamic system. What makes a closed thermodynamic system interesting is what goes on inside. We divide the universe into two different components. We'll represent the division as a circle, but it could be a divider down the middle, any number of configurations. On one side of this divider is the so-called system, and on the other side is the surroundings. The system and surroundings can each contain energy. Together, they make up the energy of the universe. In fact, the two energies add, so that the energy of the universe is precisely equal to the sum of the system energy and the surroundings energy. We can put that into an equation here. Energy in the system plus energy in the surroundings equals energy in the universe. Notice how this equation says nothing about whether the energy in the surroundings has to be the same as the energy in the system, or what form the energy in each takes. It only says that the energy of the universe is a constant, and the sum of the energy in the system and the surroundings has to equal the universe's fixed amount of energy at all times. We can say this in a more compact way, namely that energy in the universe is conserved. What we've done here is to formulate the so-called first law of thermodynamics, which is also known as the law of conservation of energy. The first law, as I've said, says nothing about what form the energy might take. In fact, energy can take many forms. It can be electrical energy, it can be heat energy, it can be pressure, or it can be concentration. All of these are forms of energy, and we've known since the middle of the 19th century that these forms of energy are interchangeable. Electrical energy can be converted to heat energy or pressure, and so forth. We'll come back to the implications of this interchangeability in a moment. For now, all we need to say is that the first law places no constraints on how this energy can be converted from one form into another. This is where the boundary between the system and surroundings comes in, because it's the boundary that manages the conversion. We might say, for example, that heat energy could flow from the surroundings into the system and be converted into electrical energy. In this sense, the boundary might be considered to be the machine that does the conversion, say a steam engine that powers a generator. The flow of energy could as easily be in the opposite direction, say the conversion of electrical energy back into heat, like in a space heater. All the first law says is that no matter what the conversion is, or what direction the energy flows across the boundary, the sum of the energy in the system and surroundings must always equal the energy of the universe, which is fixed. It is conserved. Okay, that's the first law. There is, in fact, a constraint on these flows of energy back and forth between the system and surroundings. That constraint is embodied in our next law, the so-called second law of thermodynamics.